Greetings, this is Mark Anderson for Kellogg Community College, and we're going to be looking today at some of Introduction to Functions and a little quick review over some of the concepts that we've learned before in part one of this three-part video. Talking about functions, talking about one-to-one equations, and all types of domain, and some set notation. So here we go with kind of a potpourri of different topics surrounding functions, equations, and graphing. Now, as a quick reminder, the domain is going to be all possible x values, and the range are all possible y values within a function, or an equation, or any kind of pattern that you see. So when we talk about domain, we're going to talk about the possibilities of x, and when we talk about range, we're going to talk about the possibilities of y. It would also kind of benefit us to talk about what is a function. And a function is, for every value of x, there is one value of y. And the test for this is something called the vertical line test, or abbreviated as VLT. The vertical line test says if I have a line or an equation, it is a function if the vertical line only touches it at one spot. So as I continue to draw this wavy line, as long as it doesn't split in two directions at once or double back on itself, it's considered a function because it passes the vertical line test. A vertical line will only touch it once. This also means too that the equation can kind of move, can change spots, and then continue going. And we use these open and closed circles to show that there is no overlap, so the vertical line would only actually cross one solid point at another. Of course, you can even have a function stop and then start again and keep going. We're going to see a lot of different types of functions, and in the third video, we're going to actually look at piecewise functions. Now, if we have a one-to-one equation, notice I said equation, the one-to-one equation, for every value of y, there is one x, which means that this is something, and if I kind of show this tornado-ish swoop here, this is the horizontal line test, or abbreviated as HLT, which means that at any one point, or any horizontal line will only intersect it at exactly one point. So as long as it doesn't split into or double back on itself, this is a one-to-one equation. And we're going to take a look now at some examples of something that's a function, but not necessarily one-to-one. So that would be kind of my swoop right here. This is an example of a function that is not one-to-one, since it passes the vertical line test but fails the horizontal line test. The one-to-one function would be something like so. It would pass the horizontal line test but fail the vertical line test. Both would be a kind of straight line that would not actually undulate like these curves. This straight line, I try to draw it straight. This straight line, as long as it's not horizontal nor vertical, it is both one-to-one and a function. And neither would be any kind of circle or loop or something that would double back on itself in both ways, horizontally and vertically. This is an example of something that is neither a function nor one-to-one. So for our final part of this worksheet video, we're actually going to spend a lot of time on technology, because it says here, using technology to determine the domain of each function. Make a quick sketch. Use algebra to show exclusions, and try to find patterns. Well, let's actually remind ourselves again that functions means that we are going to look at something that passes the vertical line test. Moreover, we're going to look at domain, so I'm going to bring up my graphing calculator here and type in the equation. Let's go to y equals and type in the negative 2x plus 1. Notice I used the negative key by the enter key. It's not, even though this does look like a subtraction, it's a negative. And I'm going to make sure that I have nothing else in my, well, actually, I should ask all of you guys to reset your window by clicking the zoom button and then the number 6 for standard. And this would give you a window that's negative 10 to 10 on x and y, going by a scale of 1. So again, that's zoom 6. You only have to do that once per worksheet, and now it's set up. And there's my picture of that. There's my little picture of this. Now it says to make a quick sketch and then to use algebra to show exclusions, probably when finding the domain. I'm going to do one problem at a time, and every time I change the calculator, all of this work will go away. So you may want to copy it down as we're doing it. When we look at domain, because well, when we look at domain, we're looking at all possible x values. So on our little quick sketch, which we don't need to actually plot points, that quick sketch shows that this is a line that just goes forever and ever and ever in both directions. So in terms of domain, it's infinitely wide. So therefore, if I use my little set notation, Alfred Hitchcock face, x is knocking on the door, and x belongs to the set of real numbers. So x is an element of the real numbers, and this is a way to say that x is all real. We use this little x knocking on the door because this is an infinitely big set, and that is pretty straightforward when you have a straight line. As long as it's, if it's horizontal, if it's increasing or decreasing, you're going to have all real numbers. It just can't be vertical, and that's exactly what we have here, a nice linear graph. Now in problem number 2, we don't actually have a linear graph. I'm going to change that to 3x squared plus 1. And we're going to hit graph. We're going to see this is a little bit of a pitchfork in terms of its shape right there. So that means that we are again going to make a quick sketch of this. And quick sketches, unlike my other homework assignments when I ask you to make a drawing, I'm not really asking for points. I'm just asking for you to see what kind of picture this is. And this is a smile that goes up forever and ever and ever. It just keeps going and going. And this little quick sketch right here now is relating back to this idea that here we have a graph that gets bigger and bigger. So this is another problem where x is all real numbers. This gets infinitely wide. We're not talking about range, we're just talking about domains. So this graph does eventually go to negative infinity and positive infinity as it gets wider and wider and wider. Now we're going to start actually running into some problems with the next graph here. On my third of 5 graphs to finish up this video here, I am going to have 6 divided by x minus 5. Now you have to put the denominator in parentheses, because if you don't put the denominator in parentheses, it's going to think it's 6 over x, and that quotient is then going to get subtracted, or you're going to subtract 5 from that. And that's not what you want. You want 6 in the numerator dividing by the binomial of x minus 5. And here's what you get. You get this weird graph that kind of like goes down, 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 and then it kind of comes back up to the top here and goes again. Now, in newer calculators, you may not see this vertical line. You got to imagine that these older calculators are kind of like Etch-a-Sketches, where as they go down to the bottom, it kind of drags the stylus up and then continues drawing. This is not an intentional asymptote line, but it is actually an asymptote line at that excluded value, because if I go to my graph here, or sorry, if I go to my table and I look at that value of 5, there's an error. 5 doesn't actually exist in this function here, and that's because if I plugged 5 into this equation, I would get a division of 0 error. 6 divided by 0 by plugging 5 into this equation would be undefined. So this this function isn't all real numbers. This function actually has a problem. And again, let's make a quick sketch of this. If I was making a quick sketch, this would go down here and start up above here. Now, I would probably want to put in an asymptote line that was a line that this function cannot cross. And again, this older calculator shows kind of a calculator error to kind of drag that stylus all the way up and draw that line. Newer calculators do not show this. So this is maybe where the older calculator has a slight, nod for if you know what you're talking about here. All right, so now how do we talk about the set notation for the excluded values? Well, what I'm going to do is I'm going to take my x minus 5, my denominator, and that can't be 0, because denominators cannot be 0. So therefore, if I take my denominator and set that not to 0, and solve for x by adding 5 to both sides, x cannot be equal to 5. So my set notation is going to be x, where x cannot be equal to 5. Now, you do see sometimes books say also that x is an element of real numbers, but I might not be that picky. As long as you put down the excluded value inside the set notation, I'll be okay with that. But we really probably should, for the best math grammar, say that x belongs to the set of real numbers as well. That way we don't assume that you could have an imaginary number in for this problem. Well, we got 2 more problems to go and 2 more kind of tricks, because in this case we're going to have, clear that out, we're going to have the square root, and the calculator puts in that parenthesis, which is so nice, 4 minus x, and then close it off there. So the square root of 4 minus x, let's go take a look at the graph. So in this case we got a graph that kind of goes down, 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 and right around this x equals 4, or 4 on the x-axis, it looks like the graph stops. Now the question becomes is like, does it actually stop at 4 or does it stop before 4? So if I take a look at my table, you can see that there's actually a value at 4, but there's no value after 4. And the main reason for this is that square roots cannot be negative. Square roots have to be positive, and so therefore we're going to have to come up with another rule like we did for the denominators here. So square roots have to be greater than or equal to 0. And we say that because we have a graph here that stops existing at after, it seemingly stops existing after 4. So let's actually do that algebraically. The inside of that square root has to be greater than or equal to 0. So let's use a little bit of algebra to solve that. Subtract 4 from both sides. Negative x is greater than or equal to negative 4. Divide by negative 1. And a little bit of basic algebra to remind you, when you multiply and divide by a negative, you have to flip the symbol. So the symbol gets flipped. Whoops, I didn't flip the symbol. Ha ha! Alright, so let's try that again. When you multiply or divide by a negative, you have to flip the symbol. There we go. So now we need this is actually our domain. Our domain is x is less than 4. So if we have our set notation, x is less than or equal to 4, you can also say that x is an element of the real, or x is a part of the real number system. But again, this is going to do it for me right there. I'm not going to talk about real numbers unless that was the only situation, like in problems 1 and 2. So x is less than or equal to 4. Well, we can definitely see that. I mean, there's 4, 3, 2, 1, and I bet if we had a table value that was higher than 4 but lower than 5, like 4.1, it would also say error there. So to remind ourselves here, because we're going to need to, in problem number 3, denominators can't be 0 and square roots have to be greater than or equal to 0. So what would happen if I took the combination of that? What if I took for my last problem here, what if I took a denominator that had a square root? Okay, so here we go, typing this equation incorrectly using my parentheses to establish that I want the square root of x plus 5, that binomial, square rooted in the denominator divided by 1, and here's my picture. Looks like that picture is starting somewhere over here above the negative fifth part of that number line. So let's go draw a quick sketch and see what we can put together here. Alright, so here's a quick sketch. We have somewhere over the 5th dot this little curve right there. And again, this is all I want in quick sketches. We've plotted 5 points or more on previous worksheets and videos here. But now I want to really investigate on how do I algebraically solve for this excluded value. Well, so far what we learned is that the denominator here, that denominator cannot be 0. And square roots here, that's the thing in the square root, has to be greater than or equal to 0. So what happens if we have something that can't be 0 and also has to be greater than or equal to 0? Or it can't be 0 and it has to be positive. This sets up our final rule. If we have a denominator and a square root, that denominator and square root has to be greater than 0. So it's kind of like combining both restrictions. Like, hey, what do you want on your pizza? Oh, I don't want 0 on my pizza. Hey, what do you want on your pizza? Oh, I just don't want any negative numbers. Well, if you don't want 0 and you don't want negative numbers, then we're going to make sure we're bigger than 0. And then everybody's happy with that pizza. So we're going to subtract 5 from both sides. X has to be bigger than negative 5. Go to my set notation, x is greater than -5. But wait, can I actually verify that on the graph? I mean, it looks like at -5, it looks like it starts there, but because the resolution is so poor, maybe it actually exists and I got the problem wrong. Well, what I'm going to do to close out the video here is I'm going to show you the table. All this work's going to erase. But if I show you the table, and the table says error on -5, then we got our hypothesis right. And here we go at -5. The big reveal is error. So we got it right. This graph is definitely greater than -5. So any value above -5, like -4.9 or -4 or -3, the graph will exist because 4, the square root in a denominator, that key piece inside the radical needs to be greater than 0 because it can't be 0 and it can't be negative. Well, thank you for watching this video and the little quick steps here. Hopefully you learned a lot. And there are 2 more videos that are going to cover this review of functions. So stay tuned for those. And as always, thank you for watching.